Designing and programming distributed system is a very complex topic, and guess what? There is a book about it. It's rather new. This book, which is named Designing Distributed System, is by Bernard Burns, and in this book he has some thesis. This book is not that long. Today I will share with you my notes from reading this book and what I learned from this book. I really recommend it. So he has some thesis, as I said, in this book. What he's saying is that patterns have emerged. The first patterns in computer science have emerged with Donald Knuth. And Donald Knuth have written the book The Art of Programming. Okay? The Art of Computer Programming. And in this book he has laid out the foundations for algorithms. So the basic algorithms that he used, like Q, stack, and all the basic functionality from programming languages, what is a function, how do you call it, what is returns, all this stuff was patternized. Okay, it was patternized by Donald. And now we have all these patterns, and then the software systems have become more complex, and then came the Gang of Four. Okay, and they have created the Design Patterns book, which is a set of patterns for mostly object-oriented practices. So they have patternized object-oriented programming. And then came distributed systems. And with distributed systems, you need a whole new set of patterns. So people have much speciality in distributed systems. And there are patterns, but the author tries to summarize this pattern. He says, okay, we know that a programmer with 20 years of experience in distributed systems can create such system, but can I write a book only 165 pages and lay out all these patterns? And this is what he's doing. So I'm not saying this is equal to the previous book, but this is at least the thesis and what this book is trying to do. Okay, so it's not a deep dive into distributed applications, but he will show you what are the distributed programming patterns and how you can use it. Being patternized. Okay. And with that, I will begin scanning the book first by its content. Let's see what's the content of this book. And later on, I will show you simply my notes from this book. So he started with a brief history of system development, and you know what we said about Donald and the art of programming languages. Then he starts in part 1 talking about single node patterns. These are patterns that you can utilize in a single node, but not necessarily. They are also useful for multi-nodes. But before we dive into multi-nodes, we start with single nodes. So in single nodes, let's zoom in a little bit. In single node, he has the sidecar pattern. The sidecar pattern is today it's used as a container that you put beside your application container. So you have a pod, and you put another container, for example, for aggregation of logging, or for aggregation of monitoring, or for TLS termination, for logging, whatever. You put this sidecar pattern. Here is an example with an HTTPS about how to do this, and this is the first pattern. So you already see that he uses Kubernetes. I mean, the sidecar pattern is mostly talked about when you talk about containers. And today, the de facto container orchestration framework is Kubernetes. and he will present to you with actual examples how you create the sidecar pattern, what it is and how you do it. The ambassador pattern is more for communication in between containers. So this is the next pattern, and then there are adapters, which let's say you have an application and it exposes and is alive or a health check in one convention and you want to adapt it to a different convention, so you use it. So here he adds a rich health monitoring to MySQL, and note that he's doing all this with Kubernetes. So it's somewhat amazing, it's somewhat mind-blowing that you can take a programmer with take 20 years experience, or you can take a programmer with, let's say, with 1 year experience or none. He will read this book, he will learn how to use Kubernetes, and he will know how to apply patterns of distributed computing, simply with utilizing the orchestration. This is the theory. Remember, we said we had first Donald Knuth with the art of programming languages for formalizing and doing and giving us the patterns for the basic algorithms. And then we had the Gang of Four with the design patterns book, which have given us the design patterns for object-oriented as system has become more complex. And today, when systems are mostly distributed, then we need a new set of patterns which was already proven to work by all these other 20 years experienced software developers in distributed system. So then he moves on to a part 2, which is serving patterns. In serving pattern, it's how you serve your data, how you serve the request. So here he talks about load balancing, replicated load balancing, about stateless and stateful and caching layers. And then about sharding. Sharding is the art of splitting either the data or the computation. It's not necessarily about data. Most people think it's only about data, but sharding simply means that you take a set of data or computation and split it. But you say all data between 0 and 10 goes to this shard. All data between 11 and 20 goes to this shard. And then scatter gather, which you know mostly from MapReduce. It's a kind of sharding, so you scatter your computation and you get it back. Functions, which means there is the concept of serverless or functions and events. Ownership, elections, which is sometimes the first topic which you hear of in distributed computing, which means you need a master. He first asks whether you really need a master or not. Then about work queues, event-driven, coordinated batch processing, and a summary. It's very important to notice that he's doing all this with Kubernetes. So he's taking all these patterns. He's not writing much code. When he needs a lock, he uses some ready-made service, for example, a key value store. So this was our first part of this introduction to this book, Distributed Design and Distributed Systems, and now we'll go for a little bit of a deep dive into the book. Okay, so let's start discussing so splitting first your code base. So he says that there are advantages and disadvantages for splitting your code base. You can then serve multiple teams and you can roll out versions of one components faster or separately from one another. But he also mentions, and I like it, he also mentions that there are problems with microservices. The main issue is that you are not really aware of all the microservices. If you need to troubleshoot, it's much more difficult. Okay, how do you trace the transaction? I mean, you started in server A and you finish in server Z. Okay, so debugging and troubleshooting is much more complex. But you get some benefits. So if you are living in distributed systems with multiple teams, you probably need microservices. If not, maybe not. And then he moves on to the first pattern, which is the sidecar pattern. A sidecar pattern means that you have an application container, which does not interact directly, but sometimes through a side container. For example, if you need to write logs, then you don't send them directly to the log aggregator. You always send your logs to, let's say, localhost and some port. Okay, you send your logs to some localhost and some port, and this is the sidecar container for logs. He will take care of shipping the logs and everything. So the sidecar containers are co-scheduled into the same machine and into an atomic container group, which is the pod. So the pod in Kubernetes has your application controller, application container, plus sidecar containers. So imagine someone builds some sidecar containers and you just package them, and here you have removed some logic from your app, like monitoring, TLS termination, into the sidecar. So this is the sidecar pattern. And even for configuration, you can tell that your app will load config from disk, and you will have a sidecar container which will listen to remote database and update local file system and notify the application container about configuration changes. Sidecar container. So when an external service tries to contact you, the adapter can return a standard response. This is simply the adapter. Yet another pattern. Now note that all these patterns he's describing them in the context of an orchestration. In our example, he's describing all these patterns in the book, in how to implement them in Kubernetes. So again, imagine if you didn't have Kubernetes, you would need to implement some adapter or another application or another process. The orchestration is making it very easier. I'm not saying it's not possible. Of course it's possible. 99% of the world is doing it without Kubernetes, but it's interesting to see it from this view. Next, he is talking about microservices and load balancing, and these are not news or breaking news, so I won't elaborate on this. He's just saying how you scale up with having more replicas, and you have a probe which informs the load balancer to increase the cluster capacity, and you always start by adding some kind of URL to any of your services. Your services like is alive or health check, okay, and it's always a good practice to add it even if you don't have yet the system which examines it. And in this way the load balancer will contact your application, check the health check if it's working. If not, then maybe raise another replica, replicate the stuff. And remember, you need to have this process which checks if you are alive or not. So with Kubernetes, then of course you have the concept of sidecars, and they can check whether your service is alive or not. They can check the CPU, they can check many things. and the load balancer will simply send the request to the correct server. And we talked about sharding, which means that you can have an adapter which will forward the request to the right shard or SSL termination. So it all comes together, and Kubernetes, although it's very much complex, is helping you with this. Next, it talks about sharded services, which is very much like sharded data, only it's for logic. So when you have some logic, when you need to do some request, then you might need to choose a server to send your request to. And if you have like replicated services like replicated data or stateless, then you simply choose one of them. But if your servers are storing some data in cache, then you want to direct the request to the specific server. And if you direct it to the correct server, then the data will already be in cache. So in this way you can have a container which is responsible for finding the correct server to send the request to. And you have all this logic about consistent hashing versus standard hashing, and how consistent hashing is better. It's not the main focus of the book, but he discusses it. And the problem of hot sharding, which means that you might get one shard. You might have one shard which takes lots of traffic because maybe a very famous actor is in this shard or in this cache bucket. So what he suggests is that you dynamically grow and shrink and move responsibility in between the shards. Next, he discusses scatter gather. Scatter gather reminds of MapReduce. In this, you scatter your computations to many leaf nodes, and then you get back the results and you aggregate them. So you don't have a meaning for a result until you gather the results back. Again, he discusses it, how to do it in the context of Kubernetes. Next, he discusses functions and event-driven processing. He reminds us not to be perplexed by the multi-definitions of functions and event-driven. Event-driven can live without function or with functions. By functions, he means the serverless concepts, and serverless can live with or without event-driven. These are not two technologies or two concepts which are the same. They are separate, but one can have the role of both. So in here, he says that it can be tempting to see one solution like the event-driven or the other like the first one. Also, it can be very, very tempting to think of the event-driven processing as a single hammer to bump on all your nails. And this is not necessarily the case, because event-driven systems are very complex. And you should do a lot of thinking before you use them. It's simply too much complex to use event-driven processing. You do it only as last resort. I mean, you don't jump to event-driven system because they are cool. You do this because you have to, because your system behaves like an event. It's like you don't prefer the is, has, to, is, you don't prefer one to the other. It's a misconception. You use one when right, and you use the other one when it's right to use the other right. With event-driven, it's very difficult to see an overall sequential processing of your system, how it's working. Also, you can have some bugs of loops, because if function A calls function B, and remember those are two separate processing, and then function B calls function A, you can have a loop, and this will take all your resources and maybe all your money, because if you are paying for this service as a function, as the number of calls per function in server less, then you really don't want this loop. But if this loop was simply in EC2 instance, then it would be simply a 100% CPU and not a hilarious number of calls from an infinite loop into your functions. In his mind, the difference between events and functions is that functions are more of stateless thing. You run them and get rid of them. And in servers you have a state. So as events are inherently stateless, in many cases they are stateless, and also they are independent. In many cases they go very well with functions. And how does that relate to Kubernetes, you ask? Because Kubernetes handles very well functions, serverless functions. So this is another case where you can use serverless to run your event-driven logic on top of Kubernetes, which is yet another design pattern in distributed systems. Master election. First, you need to check whether you really need a master election, because you can have a very high availability even without a master election, which means if you have a single master, and why do you need master at all? If you have some operation which you need to take, that it will take place only on a single node, like a singleton. So if you had a single node, you simply would create a singleton. But if you have multi-node, you cannot create a singleton. So you need to elect a master, but only if you really need a master, because in many times you can simply specify that one specific server, a very specific server, is your master, and that's it. You don't really need to re-elect another master unless you need really a real high availability, so you need to re-elect the master. So instead of re-implementing master election, you already have the building blocks. Many key value stores already give you compare and set, and you can say that a specific key, this is the special operation, has the master node name. So only the master node name is the one, and you attach also a TTL, so that if the master does not renew this key, then you will remove this key, and in this way you achieve a master election. So Zookeeper gives you this ability, etcd gives you this ability, and many such services. You could also think of it as a transaction. You lock something in the database or somewhere, and if you locked it, then only you own it, but you lock it with a TTL. So this is not, of course, the whole story, and there are issues to handle, which is, for example, versioning. You want to make sure that you have locked the node, so that when you come to unlock it, then you check that you have still the same version, and not that you went down and another server came up and took your lock. So he discusses it, and the basic building block to do this in Kubernetes and in orchestration is simply to use the ready-made key value stores. And etcd you already have. This is the actually etcd is managing Kubernetes in the same way. This is it's used for locking and for the master election. Next pattern is batch computational patterns. So it has here a few patterns. The first of them is a work queue system. If you already have some experience in this area, then you already have some knowledge about these systems. Nothing really new here. The only recommendation is that when you design some API, you put a v1, and when you put a v1, even though you don't have v2, you're already using versioning. So if you change your API, so basically you have your queue and you distributed your load. And you can utilize Kubernetes for that. How can you utilize Kubernetes for that? Because Kubernetes already has the concept of job, which is something that wakes up, maybe takes some item from the queue and runs it. So you have the building blocks, you have the locking, you have maybe the master election in order to specify the place where you hold your queue, and with this he comes to event-driven batch processing. So we had event processing and now we have event-driven batch, which brings us to workflows. Here we take an item from the queue, item 1, and then when we finish we put an item on the queue, and then we have item 2, and it's a process. It's a directed cyclic graph. It's a workflow system, and you have here many patterns, like the copier, where you need to do maybe a video transcoding, so you transcode it to 4K and also to 1080p. You have the filter, where you have multiple work items and you split them. You have the sharder, where you split your work items into multiple shards. So you split your work. This is very similar to handling streams. You have filtering, you have merging, which is like the reduce step. And the way to do this is how he does hands-on, is actually to install the Kafka, which is very easy to do it with Helm on a Kubernetes cluster. So you install a Kafka and you can change the capacity or the number of nodes in Kafka very easily done. You just run kubectl, at least for a POC, yeah, not for real production. They run Kafka consumer, and same kubectl run Kafka producer, and you have a Kafka running up and running in Kubernetes. So Helm gives you the images and you simply run it. So you have even a event-driven batch processing workflows. Of course, you need to write the logic to sync them. Coordinated batch processing is the next topic. Coordinated batch processing. Here you wait for a join. It's like a reduce. It's like the reduce step or join, where you cannot really return the whole of the result unless you have something which is called a barrier synchronization, which means you have some kind of barrier. You do all your computations, but you need to wait for the final result. You need to sum it up. It's called reduce because you are reducing. Usually you have 1 1 1 and you have reduced it to 3 if it was sum. So you wait and you do the join and you coordinate through the join to ensure that no data is missing. You do the coordination to ensure no data is missing before you do your aggregation. Okay, and in the sharding phase, the previous phase is like the map. Sharding phase is the map where you split your work, and here you join it.